record, and now it looks like there's sound on that as well. And you can still see both screens.
Yes,
Okay.
one's in front of the other, but yes.
Yeah. Well, we can actually stop sharing. We can stop sharing this this terminal thing. So now we just have that, right? Right. So we need to do chapter 6. There's nothing super complicated in chapter 6. Most of it is basically stuff you already know. But it's my experience that there's some of this stuff that people are a little shaky on sometimes. So it might be a good idea to go through it. So we'll do that. So let's talk about name resolution. And scoping. And one of the things that we often have to talk about first is just activation records or call frames or whatever it is you're used to calling them. And let's just do that. So I don't know. I always forget what Ed calls them, but I call them an activation record. They're called frames and stack frames and environments and similar things, right? What is that? What's an activation record? What do I use it for? What's in it? So what is its use and content? Anyone want to say something semi-sober about that? No? Well, when you run some code, so if I write a little program over here, so let's just do an example here. For example, I don't know, int f, int n, double m, double I equals something, I equals n plus m, return I. Well, that's a pretty bad program because that's never gonna fly, but that's okay. So when we run this, when we run that, we need access to my locals and my parameters. And they live in an activation record. So the content is locals, params, use, I suppose we could say each method call has one. No, I don't know how to fix your microphone. Sorry. Unplug it, I guess. This is probably the only way you could sort that out. But what else do we have in an activation record? There's a few other things that you probably remember from other classes, right? We've got some pointers. We might have a return address and a whole bunch of other stuff, right? So why do I need them? Why can't I just say when I compile this code here that this n here, oops, this n gets some address, this m gets an address, this I gets an address, and then everything is fine? I mean, I could just have the compiler say, well, I'm going to set aside some room in the stack area, and say that address n is at an offset of something from some given stack pointer at the beginning of the program. Why doesn't that work? Why do I have to go through all these hoops to introduce activation records rather than just being able to say that n, m, and I live at some offset off of a stack pointer? Anybody got any recollection of why that is? Yeah, multiple n's and m's and i's cause certain issues. Like what? Well, if you have recursion and you say that m is off of some stack pointer, then all the n's are going to live in the same place, all the m's are going to live in the same place, and all the i's are going to live in the same place. Whereas if I have an activation record, so let's just I'll draw one here in green. So there we go, and we need room for an integer and two doubles. Let's say this is at 0, at 1, at 3. Well, I'll put the other ones in as well. 2, 4. And this is where n goes. N is an int, so 32-bit. Here goes m, that's a double. That's 64-bit, and that's I. That's also a double. Now, if this address is relative, well, actually, all of them are relative to the location of the entire activation record. Then it's fairly easy to just create another activation record, throw on top of this one, move the stack pointer, and then just use the top of the stack pointer to relatively address the most recently created activation record. Alex says could affect the heap as well if not designed correctly. Remember, the heap is where you put things that are dynamically allocated, and activation records live on the stack. So you might have to elaborate on that. Actually, let's just do another example real quick here. So if I go something like int fib int n, if, what is it, Fibonacci, that's 0 and 1, that gives a 1. If n is 0 or n is 1, then return a 1. Actually, can we just do another one? I don't want to do Fibonacci, it's too complicated. I'll do factorial, everybody's favorite function. If n is 0, return 1, else return factorial of n minus 1 times n. And if I say factorial of 4, and we look at what the stack looks like, so this is my stack. There is some stuff down here. I don't know what it is. It is of absolutely no importance. We'll make it look like that. And then we get an activation record for this this first call. So this is for factorial 4, and in there we have n is 4. Then we get one for factorial 3, where n is 3. One for factorial 2, where n is 2. Now we're running out of space here. Factorial 1, n is 1, and then we get finally one for factorial 0, right? Now there might be some other stuff in here as well, right? Return addresses and what have we not. We'll come back to that. Now let me do another quick little example here. Since heap grows in the opposite direction of the stack, messing around with how the stack grows could potentially interfere with the heap, if that makes sense. Yeah, well, yes, but that wouldn't be the problem here, because that only happens when the stack grows into the heap area, and that wouldn't be the case here, right? So consider the following code. Void f int n int m void g int x int y equals x plus m plus n, f of 2 down here, sorry, not f, g of 2 and f of 4. Should probably give a value to this guy here. We'll just do it like that. So if I have a language in which I allow nesting like this, and I say, all right, what does my stack look like when I do that? So I get an activation record here for f, and it has an n which is 4, and it has an m which is 6. And then what that does is it calls a g. So we get a g guy up here, and g has an x which is 2 and a y which is, well, so y is now supposed to be x, m, and n. X is right here. I can find that right there. Where do I get m and n from? Well, they're coming from here, right? And I can see those because m is there, n is there, and this is defined inside. So I got to have some way of finding my way down here, right? Because y becomes x, which is 2, plus m, which is 6, plus 4, so it's 12. And surely that's this one, that's that one, and that's that one. So we have a link here. This guy we call a static link. And it always points to the activation record associated with the surrounding, the closest surrounding code. So because G is called inside of F, then the closest surrounding code surely must be F, which means that if I'm trying to look up variables, then I can do so in other activation records, as long as they are enclosing or representing enclosing code. So now if I take this thing here, so this guy, and I'm trying to do y equals x plus m plus n, then let's say this guy is at 0, this guy is at 1, this guy would be at 0, this guy would be at 1. I'm going to call this guy SL for static link, and I'm going to say that, well, so in reality, I would probably place the static link at 0, because that way I know the static link is always at a particular address, and then I'll put the variables some other place. But you can move things around as long as you generate the right code. So basically what I'm saying here is I'm saying, well, the address at 1, so that's y, gets the value of whatever I have at 0 plus the value of m. Where's m? Well, m is at 1 if you follow the static link. So it's the value of whatever the static link plus at 1 plus the value of the static link and 0, right? So I can follow my static link to other activation records if they are enclosing code. Now, just to find my way back to where I came from, I can also have a dynamic link, and it just always points to the activation record for the caller or of the caller. Right. So is it possible that the dynamic link doesn't point to the activation record immediately below it? So could I get a situation where the dynamic link of an activation record points to something that is not the activation frame that's right below? This is where I can then use this this app that I just found last night that I forgot that I had, and I put it into utilities. Oh, I have to. I'm funny. Anyways, the answer to the question, if nobody wants to answer it, I will do myself. The answer is yes. It always points to the one below, because if you call, if you're a method or some code representing an activation record, then if you're running, you're going to be at the top of the stack. When you then call somebody, then you need to create a new activation record for that method, for its locals and for its parameters. And you put that on top of the stack, so you push a new activation record onto the activation stack, or just the stack, because that's what the stack is. And now you're no longer at the top; you're the one right below the top. So therefore, the caller is always immediately on top of the callee, right? Or below. So the callee is right below the caller. Whoever makes the call is below, because whoever is being called, i.e. the callee, is going to be at the top, because that's going to be the code running. And I guess we could also say that this point here, or somewhere, I'll be vague and put it here, is the system stack pointer. Right? So that stack pointer just grows as you put more activation records on. Right. So am I ever in a situation where I don't need a static link? Right. So, well, let me ask this here. So do we always need a dynamic link? And the answer is yes, to find the right location of the caller's activation record. In other words, the activation record on top of the stack, if you look at its dynamic link, it typically points to what the stack pointer pointed to before it was put on there. So it's just an easy way to find our way back. Do we always need a static link? And there are two situations for which that answer is no. Anybody want to take a stab at when I don't need a static link? No nested functions. You're going to add a little bit to that, but you're very close. Main doesn't need a static link. Okay. No recursive calls. No. Because if you you were closer before. So for the recursive calls, just because you can call yourself does not mean you can see the code. Or you can see the values of the variables in previous incarnations, right? So you don't get to look at sort of shadow values of n because you get your own copies, right? And no, I'm more thinking about it. It really depends, how are globals handled? Are global variables kept in an activation record somewhere? And if it is, then you could implement it by sort of putting it at the bottom of the stack. But typically globals are just kept somewhere else. So I think we'll probably go with if we'll just say if nested functions is illegal. Because if they're not if we don't allow nested functions and I did a sort of a whole bunch of activation records, we'll just stack them on top of each other here. So these are just they're just various activation records. I don't know what they are, but it doesn't really matter. And if they have a static link, so I always like to say if I have a global and if I have global variables, I'll just sort of plunk them down here. But if we I'm pretty sure the way you do globals in C and C++ is they live somewhere else. They don't live on the stack, right? No, they live in a special global segment somewhere else, right? Yep. And everybody knows how to find them. So, sure. Well, in theory, right? So where should these static link points? Well, they shouldn't point anywhere, right? So I would just sort of get something that looks like this. There's nothing to them, right? So if they don't point anywhere ever, what do I need them for? Abstract method calls. No, that has to do with virtual dispatch. I'll come back to that later on. What about number 2 here then? It's actually a much easier one. So think about what the static link tells me. If you go back and look at this page here, the static link says, all right, when I'm inside this method here, and I need this state out here, then the static link points to the frame of an F, right? Because that way I can find those guys. I can look at this code and say, okay, when this G runs, this X is that one, that X or that M is that one, and this N is that one. What sort of scoping rules is that? What do we call that sort of scoping? That's static scoping, isn't it? What's dynamic scoping? Has anybody ever written anything? Terrible. yeah, dynamic scoping is terrible. I assume that you weren't talking about static scoping there. You were talking about dynamic scoping. So if I have a dynamically scoped language, then I don't need a static link, because if everything is dynamic, then what's the point of a static link? So basically here we use the dynamic link to resolve references to variables not belonging to a particular activation record. So you always have your dynamic link because we said yes, you always have it. And in a dynamically scoped language, it's the call sequence that determines whether or not you can resolve something. So we can come back and talk more about dynamically scoped languages later on. But since most languages are statically scoped, I want to continue with that because we don't have that much time left over today. So let's just talk a little bit about name binding and scoping. And this is just sort of to get the lingo right, so that we can talk about the right things, right? So let's just look at definition 6.2, which is about name binding. So it says something along the lines of the following: a name binding and then there's a fancy N that looks like this, name entity, is really just an association of a name to that entity. So we can just say here is an association of a name to an entity. So for example, we can do an example here, 6.4, which looks like this: class, my class, int my field, void my method, int my param, int my param, and guess what? Int my local equals my field plus my param. So something like this. Oops. So this line here binds my class to a class definition, namely the one that follows after here, right? In line 2, this one here, my field is bound to an integer variable, etc. Right? So the only thing that's important to, it's important to point out here that these are not bindings, right? They're uses. So with the definition of a name binding in place, then the next thing you could do is you can say, right, actually, if I look at this code here, then when you do this use, or when you have this use of my field and of my param, then the question that arises is, well, which my field is this? Which binding spot is associated with this use? So can I figure out where my field is bound So that way I could maybe find out what type it is. And we've been doing this for so long that we just sort of look up, right? And then we say, all right, my field is right there. And my param, well, that's this guy here. And if I had something down here that used my local, it's that one there. So we have a set of scoping rules, right? So we can maybe formalize that and talk about the scope of a name binding. So the scope of a binding, I'll see if I can do the fancy N again. This is really sort of hard to write down so that it makes sense, but what do you understand as the scope of a variable, for example, or the scope of a class, or the scope of, actually the scope of any name, because all bindings are names and entities, right? So what is the scope of a binding? So what could I write down the part of a program a name can be used? That's very close, and it's the first thing I think anybody would come up with. But let me just let me draw something down here. What if I said something 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 int x dot dot dot? So if I had this, right, would it be fair to say that this and this is the scope of x, the scope of that guy up there, because in here and in here both allow the use of x, right? And yes. So it's Levy's right. The part of the program, or Levy, or however I'm supposed to pronounce that. I'm sorry if I butchered your name there. The part of the program where a name results in a reference to the correct entity, right? So if I just say that it's both of these red blocks here, then it might not be right, because if I say x in here, well, it's got to be that x, right? If I say x in here, that's got to be this x. So when I'm talking about the scope of this x here, well, it's the place in the program that when I legally say x, I actually get that one. So I think I'm just going to write it down exactly like you said it there. It is the part of the program where the name or where the name use results in a reference to the correct entity. And then of course we when we make up our scoping rules, we got to keep that in mind. But I think everybody knows how that works, right? Right. So in the interest of actually getting through this stuff, I'm going to skip to 6.4. The other stuff that I'm skipping is just something that has to do with forward referenceable stuff. And the idea of that is just some things can be used before they're defined, like methods and fields, for example. But I want to go and talk about static scoping, because that is very important. Right. So we have a definition 6.6 that actually uses this idea of a name binding. So it says something along the lines that for a language with static scoping, the scope of a name, actually of a name binding. So again, that's one of these fancy things here. That looked more like a V, didn't it? Let me try that again. Is the part of the program in which the use of name resolves to entity. So basically exactly like what we just talked about before. You could copy and paste the nicest fancy, and yeah, but problem is none of them are really that all that nice. So furthermore, these regions can be determined at compile time. They're from the name static, right? So at any time during compile time, we can do this. So should we do? Here's an example. Actually, see if I want to say something else. Now, just a note here. Note on the word scope, because it can mean what we just talked about, right? So it can mean the scope of a, and we always tend to say a scope of a variable. It really is just a scope of a name binding, to be pedantic. But it can also mean a scope. So what do I mean by a scope? What is that then? Well, typically it's a block, right? So curly bracket dot 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 something, right? I.e. Something in which you can create bindings. So for example, dot 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 int x, then I have a binding here. This is a scope, and this is the scope of x. So there's sort of the difference between a scope and the scope of a particular variable, right? Now, if I look a little closer at that, We can do that with, actually we can just do that with this example here. I think that will probably work. 6.7, I think that's what we started here, but yeah, okay. So if I just say void foo, and we'll give it no brackets, and then I will say int a dot 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 curly bracket, int b dot 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 curly brackets, int c dot 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 curly brackets. I'll see how far I want to go with this. One more. Int d dot dot dot, and then we'll close these down again. If we do something like that, then we have how many of the A scopes do I have, right? So here, 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 and here. So all these green spots here are openings of new scopes. Now, what you'll notice if I look at the relationship here between the scope of X and a scope represented by curly brackets, because this binding is done inside a scope, the scope of X also terminates when the surrounding scope closes, right? So the reason that this green line, the scope of X, ends right here is because the enclosing scope is closed, right? It's a very unfortunate reuse of the word scope here, because the scope of something is in the scope of something else. That just sounds confusing, doesn't it? But I think you already know how this works. I'm just trying to put some fancy words on it here to be a little bit more pedantic. Now, what I could do if I know, so actually let me just give these some numbers. We'll call this one number 1, this one number 2, this one number 3, this one number 4, because now I can sort of I can close them down here, right? So we have a scope that closes here, we have one that closes here, we have one that closes here, and we have one that closes here, right? So these are closings of scopes. Now, of course, if I look, that one goes with this one, so obviously this is 4, 3, 2, 1, right? So if I ask you, where in this code can I legally refer to A, and when I do, that reference resolves to this A here. So let me write down where in the code can we refer to A and get this. Well, obviously that has to be the scope of A, right? Now, what is that? Where in all this code here is it legal for me to say A? 1, 2, 3, 4. So would you say, before I do it, would you say that it's, actually I can draw this in and then do an undo if I don't like it. So would you say that it's this? So we've got a restriction here that says any block. Well, so I think you just want to say anywhere below A's definition that doesn't redeclare the name as itself. Well, yeah, that's true. So but that's sort of given in the where we get this, right? So This probably should have come in here and gone up like that instead, right? So let's sort that out. There you go. How's that? Yeah, I want it to be after the semicolon, right? Because otherwise you could legally refer to A in the declaration of A itself, and that would be a mess, right? So we get yeah. Oh, Daniel, you say up there down from behind A to the end of star one, and that's exactly what we got here, right? Yeah. So maybe something like actually. So let me just do this a little nicer. I don't know if that's nicer, but it's a little bit more correct. So that's what we get right there. Right. So that's for A. What about B? Well, so it's got to be something like this to the end of 2. And so on and so forth. And when we do that, we quickly see that it is from the end of the declaration to the end of the closest enclosing block, right? So we can basically say that the scope of a local is from its declaration until the end of the closest enclosing scope. And here, the closest enclosing scope is not the scope, it's an A scope. So it's one of these guys here. It's not one of those guys. So it's a red kind of scope, not a green kind of scope. Right. So now there's some things we got to decide. We got to decide if we're going to allow silly things like redeclaration. So is this legal? Something, 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 more stuff. Int x, something, 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 int x, curly bracket. So what do you think? Any block below A's definition that doesn't redeclare name A itself. Yes, that's fine. So is that legal? No. What about this? How's that? Yes. So there's a vote of no for that one and a yes for that one. How? Why? Are you just making this up as you go along? Why is one okay and the other one isn't? Different scopes for the yes. One is a redeclaration, not allowed. Well, you get to decide what's allowed if it's your language, right? You could certainly say this is because reasons. Yes, tell me what those reasons are. One is hiding, which is allowed. Which one is that, and why? Well, yeah, but so just reasons. No. So think about this one. If I say that the scope of a local variable is from its definitions to the end of the closest enclosing scope, then this is the scope of that guy, and this is the scope of that guy. That means we have overlapping scopes of X. That's a problem. What about this guy here? You could certainly say, oh, well, the scope of this guy goes in here, but it's a lot easier to say that the scope of this one, oops, damn it. That's the scope of this one. Now, of course, you could say that the scope of X here is all of that, which means that isn't that also? Isn't that also overlapping? Seems to me that it's pretty much the same, isn't it? Now the thing is, if we take this thing here that you all claim is legal, that can actually be handled in a much nicer way. So let's just take this and redo it on this next page. But, so if I do the following, I don't know why this thing always changes back to wanting to delete, but anyways. So let me just do this one again. Something, 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 curly bracket, something, 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 int X, something, 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 curly bracket, something, 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 int X, something, 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 curly bracket there, and a curly bracket here. So here's what I can do. While I'm traversing the parse tree, which is just sort of going through the code in an orderly manner, when I get to here, I know that opens a new scope. So what I'm going to do is I'm going to attach to this part a table, a little symbol table, probably just a hash table, name v. So this is called a symbol table. So if I do that, then every time I encounter a declaration, I'm going to enter it into the table. So we could say, upon reaching a declaration, actually what we really do is every time we find a name binding, enter it into the table. Which table? Well, the current most symbol table. Okay, so once I get this guy, once I get to this one, it's got to go into here. So I get an X. What do I get in the value column here? Well, I'd probably just get something that points back to the declaration, because that way I can always find it. Okay, well, so then when I get to here, I do the same thing, because every time I get to a scope, I get a little table like that, NV, and every time I get to a declaration, now this is the current most one, we'll enter this one into here, and this one probably points to there. So if I do that, let's say now that I'm going to put in some uses. So let's say we use X here, X, then we can try putting in some other X's here, here, and here. Actually, let me just subscript them X1, X2, X3, and X4. So X1, X2, X3, x4 are all uses of x. Can we do the following as well, just to make life easier? We'll call that one def x1, and we'll call this one here def x2. So can we determine now which of the defs can, oops, not B, can we associate each xi with a specific def xj or none? So for all these red x's, can I determine which of the blue definitions, the blue bindings, they refer to? So if we try the following thing, we'll just take a look at this x4 here, right? If this x4 is a legal reference, then I should be able to find it in the current table, right? So I can go in here and say, hey, is there an x? Yes, there is, right? If there is an x, then I can follow this arrow back and say, ah, it's that def x2. So x4 becomes x2. Oops. Definition x2. What about x3? Is it legal to reference x here? We've only got 2 minutes left, so do we use a static link and find the first? No, because there's no static link here, because this is in the same piece of code, right? Static links go between activation records. All these are not activation records, these are symbol tables. There's a big difference. Activation records at runtime, symbol tables at compile time. So x3, is it legal to reference x at the point of x3? Yes. Does it give me def x1 or def x2? It gives me x1 because x2 hasn't happened yet. But so by the time I'm referencing this x won't be in here. That means if I try to look x up in here, I'm going to fail. But I want that one. Well, that's easily solved. So I can just link these guys together, can't I? We'll just say link that one up here via some parent link. So if I do that, by the time I look up x3, this x is not in here, so I'll say, oh, there's no x in here. We'll follow this guy up here and say, ah, there it is. That's wonderful, because then x3 becomes the definition x1. And similarly, x2 becomes the definition of x. That's a pretty bad x1. And finally, x1 becomes an error, because at that point, this guy does not exist. This is not in here, so I'll go in here and say, is there an x1 here? No. Is there a parent symbol table? No. All right, fine, x doesn't exist. So if I attach symbol tables and link them through parent links at all the points where I open a scope, and then by the time I get to the point where I close it, I can then remove them again. And then I always do lookups in the current most one, following parent links back. Then I can now implement, or I have implemented, static scoping. So at this point and at this point we can close that, and at this point we can close that. And that, ladies and gentlemen, is what phase 3 is all about. This part that I showed you here with the opening and closing of these symbol tables is the second part of phase 3. The first part has to do with the stuff that's in figure 6.1, which is basically declaring all the stuff that's forward referenceable, such as classes, fields, and methods. Go take a look at the video. We can talk about all the questions that you might have on whenever we meet again. Thursday, I guess it is. I assume I won't see any of you for office hours tomorrow. So there's a question that says, what if we had an X5 in between the closing scopes? Okay, let's just do that real quick. So an X5 here. Right. So at that point, so we can just quickly here, we'll just do this real quick. So at X5, the second symbol table is gone. Therefore, the first is the current most one. Therefore, it resolves to the definition of x at x1. Right? Can I ask you another question after phase 2, after class? You cannot, because I have another class that starts immediately after this one that I have to go and do. So no can do, unfortunately. And after that, I'm going out for Colombian food, if we can find Ben. And so I guess that's it. Then I will stop the recording, and I will see you on Thursday.